Hi everyone! In this video we're going to practice using proton NMR and carbon-13 NMR to determine the structure of a molecule. So on this first slide here we have a proton NMR spectrum. Now we can tell that it's proton NMR because the parts per million scale is 0 to 10, so it's pretty small. If the scale was 0 to 240 parts per million, we'd know that it was carbon NMR. We're given the molecular formula of our compound, C7H9N. Additionally, we can use the proton NMR chart that's on Canvas to help us figure out what functional groups our protons might be attached to. So underneath our NMR spectrum, we're given some information. So we're told the exact chemical shift for each signal. We're also told the multiplicity, so that might tell us a bit about how many neighboring carbons, or neighboring protons something has. And then we're also told the area under the peak, so we can get a relative idea of the amounts of each unique proton. So the first thing I'm noticing here is that I have 4 unique signals. So if I have 4 unique signals, that tells me I have 4 unique protons. All right. Now, additionally, I'm told that the doublet at 6.86 let's see, has an area under the peak of about 2. So that will probably be due to 2 hydrogens. So I'll have 2 hydrogens that are unique. So let's say they're both like HA, for instance. I'm also told I have a doublet at 6.47 and it has an area of about 2 as well. So I probably have 2 hydrogens that are producing that doublet there. I have a singlet at 3.41 and its area is 2. So I have 2 hydrogens that are producing that singlet. And then I have another singlet at 2.16, and that area is 3. So that means I probably have 3 hydrogens that are producing that singlet. Now, let's kind of try to predict what functional groups are producing these signals. So let's start with our doublets that are at 6.86 and 6.47. So let's go back to our chart. So they're in this region, which means that they're probably hydrogens on a benzene ring. Okay. So we're going to kind of start piecing together what we could have here. And I'm just going to draw a circle in the middle of my benzene ring because we know that the electrons in the pi bonds are delocalized. All right, then let's focus on our singlet at 3.41. So 3.41, ooh, this might be tough. Okay, so we could have maybe a carbon bonded to a halogen or an oxygen. Oh, one thing that's actually not really on this chart is that X could stand for a halogen or a nitrogen. That's a little misleading. So we could have a halogen or a nitrogen. And looking at our molecular formula, we do have a nitrogen. Okay, so that could be, let's see, a hydrogen bonded to a nitrogen. And then let's look at our singlet at 2.16. All right, so that could be, oh, a number of things. Well, we know we don't have any oxygens, so we can rule out the ketone. Um, let's see. It could be just a CH3 group on a benzene ring. So that's probably most likely since we already said we have a benzene ring. So let's just draw a CH3 group on the benzene ring. And that's due to this peak at 2.16. Okay, so now we have to figure out where that nitrogen is. Where would that nitrogen be? There's a few possibilities. Let's see. Let's put the nitrogen group right next to the methyl group. And would that nitrogen have one hydrogen or two? Well, it looks like we would have two. So I'm going to put another nitrogen there. Or sorry, another proton there. I need a little more coffee today. All right, so if that's the case, let's figure out how many unique hydrogens we have on this structure. So we have our two hydrogens that are bonded to nitrogen, so I'll label those A. We have our three hydrogens that are bonded to our methyl group, I'll label those B. And then we have 4 protons on our benzene ring. Now, let's focus on the hydrogen that's at the bottom. Is that going to be its own unique hydrogen, or is it similar to other hydrogens? It's actually its own unique hydrogen. It's 2 bonds away from a nitrogen, whereas, let's say, the next proton is 3 bonds away from a nitrogen. The proton above that is 4 bonds away from a nitrogen, and then the proton at the top is 5 bonds away from a nitrogen, or I guess going the other way, it's 1 bond or 2 bonds away from a methyl group. So all of these different hydrogens are in different chemical environments because they're different distances away from the methyl group and the nitrogen group. So I'm just going to label them C, D, E, and F. All right, so in this scenario, we have 1, 2, 3, 4, 5, 6 different hydrogens. But we said that we should only have 4 unique hydrogens. So this probably isn't our structure. All right, so I'm going to erase these protons, and then I'm also going to erase the nitrogen. Oh, why won't it stay as my eraser here? There we go. I'm also going to erase the nitrogen group, and we'll show it somewhere else. Okay, so another possibility is that the nitrogen group, or the amine group, is 2 bonds away from where the methyl group is. And then we have our 4 protons again on the benzene ring. Okay, so again, those nitrogen protons we'll label A. Now let's look at our 4 protons on the benzene ring. Are they the same? Are they different? Are they all in different chemical environments? So the hydrogen that's in between the methyl group and the amine group, that's kind of on its own, so I'll label that C. And then let's look at the proton over here. It's next to an amine group, but it's definitely in its own chemical environment compared to HC because it's not in between a methyl group and an amine group. It's really only next to the amine group. So that's going to be HD. And then what about the proton above that? Is that unique, or is it the same as one of the other protons? It's unique. It has a different distance from the methyl group and the amine group compared to HD and HC. So we have HE. And then what about our last proton? Is that unique or is it the same as one of the other protons? It's also unique because it's also in a different chemical environment. It has a different distance from methyl and from the amine compared to the other protons. Okay, so let's see how many unique protons we have in this structure. We have 1, 2, 3, 4, 5, 6 protons again. But again, our NMR spectrum tells us we should only have 4 unique protons. Okay, so I'm going to erase this structure as well. So this is not correct. Oop. Oh, why won't it let me erase? Yeah, I'll see if it's letting me erase at the top. It's hard to use an iPad sometimes. Okay, there we go. All right, so the last position that the amine group could be in is directly across from the methyl group. All right, so we've got our A protons and our B protons again. Now let's see if we can figure out if this is the correct structure. All right, so the one thing I'm noticing with this structure is we have a plane of symmetry. So the plane of symmetry runs through the middle of the molecule, and that tells me that the 2 protons closest to the methyl group will be the same, and then the 2 protons closest to the amine group will be the same. Okay, so now we have 4 unique protons, and this makes a lot of sense. So now if we go through and figure out what the multiplicity of each would be, the HA protons, how many neighboring protons does HA have? Well, remember, if hydrogens are bonded to a non-carbon atom, they're not going to split any neighboring protons, so those will just be on their own. So HA doesn't have any neighboring protons. So it's going to be a singlet, and it shows up right where we would expect it to, based on our chart on the last slide. What about HB on the methyl group? Those are bonded to a carbon. How many neighboring protons do they have? So actually, those hydrogens don't have any neighboring protons because if we draw out their distance from the next proton, they're too far away. So we would have to go 1, 2, 3, 4 bonds away to get to the next proton, and that's just too far away to cause any splitting to occur. So those protons would show up as a singlet as well. And so they're probably here. Oh, and I'll write HA next to the other singlet. So now let's look at the doublet protons, and those have to be due to HC and HD. And they're in the aromatic region, so that makes sense. Let's see, now HD is actually closer to the nitrogen group, which is electron withdrawing. So those would probably be more downfield than HC. Okay, so that molecule makes a lot of sense, or that structure makes a lot of sense for what we were given. All right, so I'm just going to redraw our structure down on the bottom, make it look a little neater. And one last thing I want to do is just make sure I have the right number of carbons, the right number of hydrogens, and nitrogens. So I have, let's see, 6 carbons in the benzene ring plus 1 in the methyl group, so that's 7. Perfect. I have, let's see, 3 protons on the methyl group plus 2 on the amine is 5. And then I have 4 on the benzene ring, so that gives me 9 protons. And then I have 1 nitrogen, so that matches my molecular formula. Great. Okay, now let's move on to the next practice problem. This one is for carbon-13 NMR. And here we're given the molecular formula C4H6O2. And then notice that the scale for the carbon-13 NMR goes from 0 up to 240. It's a little hard to read the numbers, so let's see, I'll rewrite them. So we've got 200, 150, 100, and 50. Okay. So you can use this chart that I provided. It's on Canvas under Modules Study Guides. And this will help us figure out where the carbons, or what functional groups the carbons might exist in. All right, so let's see. We've got a peak at 173. So if we go to our chart, 173 is here. Okay, so that could be due to a few different things, maybe an ester or a carboxylic acid. Okay, so let's just write down those possibilities. Okay, we have a peak at 136. So let's see, 136, so maybe that's a benzene ring or a double bond between 2 carbons. I know it's not this nitrile group or an amide because we don't have any nitrogens in our molecular formula, so we can rule those out. Okay, so we have maybe a benzene ring, maybe just a double bond between 2 carbons. All right, and then we have a peak at 128. So that's kind of in a similar region. So that could also be a benzene or a double bond. And then we have a carbon peak at 17.6. So that's right here. So that tells me we just have some primary carbons or maybe some methyl groups. Okay, now the other thing we want to take note of is how many unique carbons we have. So we have 4 unique signals. And I'm actually ignoring this little peak here because it's due to probably a reference compound. So that tells me I have 4 unique carbons. Now, looking at my molecular formula, I only have 4 carbons, and that means I can't possibly have a benzene ring because we would need 6 carbons for that. So we can rule out the benzene ring. Okay, and then let's see. So let's kind of start piecing together what we might have here. Okay, so, oh, and I forgot to draw a CH3 group over here, sorry. All right, so we likely have either an ester or a carboxylic acid. Okay, so I'm just going to draw a carbonyl. And then I'm going to draw my alkene, because I know we have one of those. And then I do know there will be an oxygen on the other side because it's either an ester or a carboxylic acid. So normally we don't have any peak splitting or integration values. For some reason, we're given these peak splitting values. You can ignore those. Those aren't going to tell us anything. All right. So we have 3 of our carbons so far. And let's see, one possibility is our CH3 group could be attached to our oxygen. So we could have an ester, right? But if a carbon is next to an oxygen, it should be downfield, right? It should be kind of in this region up here because it's attached to a really electronegative atom. So it doesn't really make sense to have a methyl group bonded to that oxygen because we don't have a peak that tells us it's bonded to oxygen. So I'm actually going to assume here that we can rule out our ester. Okay, so what that tells me is I probably have the carboxylic acid. So I'm going to put a hydrogen there next to the oxygen. Okay, so then where else could the methyl group go? Well, there's a couple of possibilities. It could go on this side of the double bond. That's a possibility. Another possibility, it could be on the same side as the carboxylic acid. And maybe on the other side we just have two hydrogens. And this is where it's kind of hard to tell where that methyl group would be. So it could be either of those structures. But as long as we have the essential functional groups listed, that's the important part. So on a test, for instance, if you were stuck between two compounds, but there wasn't really a good way to tell which one it was exactly, you can just write one of them, and as long as you have reasonable functional groups and a reasonable structure, I'll give you full credit for that. Okay, so hopefully these practice problems helped. And I also have a worksheet posted under modules week 7 and on the main page of the website. And in this worksheet, you're asked to try to identify the molecular structure of a compound using only the proton NMR or carbon-13 NMR spectrum and the molecular formula. And again, your structure might not look exactly the same as the one that I got, but as long as you have something pretty close, that's good enough. And the key will be posted as well so that you can check your work and see how close you got. All right, so I highly encourage you to work through that worksheet before you take the exam because you might find a couple of problems on the exam that are similar, so it's good preparation. All right, so I will see you in the next video.